Hey everyone in the Chemistry 40 world, welcome to Unit 2, Lecture 3. We're talking about chemical bonding. Here we're talking about, is life really fair? Because we're looking in more detail at electronegativity, which may mean equal sharing of valence electrons between participating nuclei or unequal sharing. So this is page 9 in your booklet, and it's going to write in the magic tablet here. Where's my marker? There you go. Unit 2, Lecture 3, all about electronegativity. It rhymes, doesn't it? So, you'll be given electronegativity numbers. We looked at this a bit in our near the end of Unit 1, knowing that fluorine has the largest value, so there it is. And here's values of other electronegativities. Metals have lower electronegativities in general than nonmetals. And what we want to look at is the electronegativity difference, delta chi. Okay, this is uppercase Greek letter delta chi, so it's the higher value minus the lower value. We're also going to look at lowercase Greek letter delta, which means partial, which means less than 1. So, if it turns out that the electronegativity difference between the two atoms forming a bond is 0, then the atoms are of the same type. Type meaning they're exactly the same kind of atom. What does that mean? They're both fluorines, or they're both chlorines, or they're both hydrogens, or they're both nitrogens. Okay, I haven't made these Lewis diagrams. There you go. So we say then that the bond is nonpolar covalent. Some books just say covalent. That's not good enough. Better books say nonpolar covalent. That means there isn't a positive end and a negative end to this molecule. The valence electrons between the two atoms are shared equally. And we say that the bond dipole is 0. There's no positive and negative end. This Greek letter mu, I know it stands for micro, it also stands for dipole. The dipole moment is 0. So these are the easier ones, nonpolar covalent. Some say pure covalent. I've seen that too. Some say if the electronegativity difference is less than 0.4, it can be considered pure covalent. But others don't say that. I'm not going to say that. I'm going to say if the difference is 0, then it is a nonpolar covalent bond. Okay? If, however, the electronegativity difference is greater than 0 between the two atoms participating in a bond, as we see here, then the atoms are different. They aren't both fluorines. One's fluorine, one's a chlorine. One's fluorine, one's an oxygen. And the bond is said to be polar covalent. There's an unequal sharing of valence electrons in the bond dipole. We won't actually calculate the bond dipole, but it is a way to talk about the strength of unequalness is greater than 0. So, for example, here we have a bond. I don't know what the rest of the molecule is, but we got a bond between oxygen and fluorine. Fluorine is the partial negative end of this bond. Oxygen is the partial positive because fluorine is more electronegative than oxygen. So the electrons are hanging around closer to the fluorine than to the oxygen. Therefore, fluorine gets a partial negative charge. It's not a complete transfer of electrons from the oxygen to the fluorine. Not a complete transfer, just a partial separation. So the positive and negative ends of the molecule do not coincide. There is, therefore, a positive end and a negative end, and fluorine is the negative end. So this is a polar covalent bond. Here we have C and N, and the vector drawn is always drawn for the bond dipole from the positive end to the negative end. So from the carbon to the nitrogen is here's from right to left. I just didn't want you to think that always the bond dipole was drawn from left to right. BF, it's drawn from left to right. Now, as the electronegativity difference between two atoms gets larger, it becomes more and more ionic, or you can say the ionic character increases, or the percent ionic character increases, and it leads to a whole spectrum of bonding. So, for example, if I had BF versus OF, well, they're both going to be polar covalent bond, but in OF, the delta chi is what, a half, and BF, the delta chi is 4 minus, what's boron? Is it 2.5? Let's take a look. Go up here for a second. Boron is 2, right? So it's 4 minus 2. So it's 2. So there's a greater electronegativity difference between boron and fluorine, so it's becoming more ionic-like. It's not an ionic bond completely yet, but it's becoming more like an ionic bond than OF. Fluorine is the partial negative, oxygen is the partial positive, fluorine is the partial negative, boron is the partial positive. I made the partial symbols, the lowercase delta symbols, a little larger in the BF than the OF to signify that there's a greater unequalness. We talk about unequal sharing all the time. Let's say you have a Kit Kat and I come and say, hey, let's share the Kit Kat with the 4 sticks. And you say, okay, and you give me 1 stick. Yeah, you're sharing it with me. That's not equal sharing. Give me 2 sticks. That's equal sharing. Give me all of it. Well, you'll get 100% on this test, right? Okay. Ha. So often you don't even need the electronegativity numbers when you're referencing to fluorine. You just say, well, the greater distance across the periodic table between the atom you're looking at and the fluorine means it's going to be more ionic-like. I mean, if I go to lithium fluoride, that's a bigger distance along the second row. What was lithium, 1.5 or 1? Let's see, let's scroll up. Lithium is 1.5, so 1.5 minus 4 is 2.5, but you take higher minus lower, so 2.5. So for LIF, delta chi is wait a second. Fluorine is 4, oxygen is 3.5, nitrogen is 3, carbon is 2.5, boron is 2, beryllium is 1.5. Lithium is just 1, right? Did I say it was 1.5? Let's go up here. Lithium, just want to be sure on these things. 1.5? I don't think so. Lithium, beryllium. Okay, so now let me go to my periodic table. We're going to solve for this, don't you worry. And I got fluorine 4, 3.5, 3, 2.5, 2, 1.5, 1. Lithium should be 1. Okay, so let me go back to my notes. Again, you'd be given these values. Bang. Okay, so the value is going to be 3. LIF will be 3. Okay, so that really is an ionic bond. Okay, so you'll have some practice on that. Now the second part of today's lecture is on molecular geometries, how we're going to arrange the nuclei in a molecule. Some people call this the molecular shape. I don't like calling it that. Molecular shape is really how the electron cloud is looking. Yes, it's associated with the geometry, but it's not exactly the molecular geometry. It's a slightly different concept. So when you think of geometry, you think of bonds, length, how long a bond is, and how one bond is situated relative to another, called the bond angle. So we're going to look at bond lengths and bond angles. And if you have 2 atoms, you don't really need to talk about the geometry. If you're talking about carbon monoxide, well, you know that's a linear molecule. There's only 2 atoms, right? But if it's carbon dioxide, it might be linear. In fact, it is. But maybe it will be bent, maybe off at an angle. When there's 3 atoms, you don't know. Anything more than 3 atoms, you don't know unless you can invoke some strategy, some model. In fact, it's called the theory by many people, the valence shell electron pair repulsion theory, VSEPR, developed in Canada by Ron Gillespie and a guy Nyholm, and Gillespie worked at McMaster University, and I actually took a course from him way back in 1985. So how about that? So I knew this guy. And he's quite famous, and Vesper's the reason why. He said that valence electron pairs will maximize their distance from other valence electron pairs to minimize repulsion between the pairs. Not within the pairs, but between the pairs. So you use the Vesper game for triatomic molecules and higher, but only for covalent systems, not for ionic systems. The lone pair electrons are irrelevant to the Vesper game. It is the focus of the central atom. What's happening on the central atom? That's important. Okay, I don't know why that mini review's there. That was, maybe should have gone a bit earlier. So anyways, you can do page 11 for mini review. Now let's get back to Vesper. So Vesper, we talk about the number of electron groups around the central atom. And that's going to be the number of bonding groups around the central atom plus the number of lone pairs around the central atom. So that's called the number of electron groups. Sometimes we call it the number of Vesper groups. Some older books called it the number of structural pairs. Some books call it steric number. So you'll hear different terminologies for this business about how many groups there are and how Vesper really works. If there's two groups around the central atom, we use a spherical system here. Think of this as the nucleus, and each group has a little block here. So the two blocks try to go as far away from each other on this globe here. So that's 180 degrees to each other through an equator or through an axis, through any radial value to be 180 degrees. So the bond angle is 180 degrees. Carbon dioxide is an example of a linear molecule. The electron groups go 180 degrees. The molecule itself is 180 degrees. BeF2 is one we didn't talk about. It's an exception. It's really weird because first of all, there's only 4 electrons around the beryllium. Second of all, it's a metal and a non-metal, yet it's still covalent in the gas phase. Well, so that is a weird exception. But in terms of Vesper, you have these two pairs and they try to get away from each other as far as possible. So that is a linear molecule. HCN, that's a linear molecule. The triple bond counts as one glump of electrons, and the CH another glump, and those two glumps try to get away from each other as much as possible to be 180 degrees. If there's 3 electron groups, then you slice through the center of the sphere, so you get a plane, a circular plane, and the electron groups, whether the lone pairs or bond groups, bond group can be single, double, or triple bond, go 120 degrees to each other. That's the best these groups can do to minimize their repulsion, maximize their distance apart. So these are all 120 degrees. And this arrangement of the groups is called trigonal planar. Some books call it triangular planar. Okay, so BF3, which has 3 groups, 3 bond groups, no lone pair, but it totals to 3. So 3 electron groups or 3 Vesper groups means that the electron group geometry is trigonal planar. The molecule is trigonal planar. You can build these models. Maybe you did in grade 11. You used marshmallows and pipe cleaners and toothpicks and licorice sticks and all sorts of fun things like that. If we have 4 electron groups, then the electron group geometry is tetrahedral, and we see it's not like a cross or a plus sign. We're using the 3 dimensions here, and the bond angle trigonometry can show it to be 109.5 degrees. So that 109.5 degrees, sometimes I just say 109 degrees, that is known as the tetrahedral bond angle. Okay, 109.5 degrees. So carbon tetrafluoride is like that. You see I've drawn a little perspective sketch. Some kids have problems with these. Just do it like this. Well, if you take art class, you're okay. Here a C and 2 F's are all in the plane of the piece of paper. Then I have this wedge coming out with this fluorine closer to you, so that makes it look like it's in 3 dimensions. Then I have another fluorine sneaking back here. So that is a good way to draw a 3D perspective sketch. Some people draw it like this. They have C, F, F, and the fluorine coming out, and then they have these little dashes going back. I don't like doing it this way, but I know some people do, and if you do, go ahead. So there's the fluorine going back. Notice the angle is more than 90. It's 109 degrees. You aren't confined, 109.5 degrees. You are not confined to an angle of 90 degrees because you aren't confined to 2 dimensions. You get 3 dimensions, so it's a tetrahedral bond angle. If you want a lovely graduation gift from your friends and family, ask for a molecular model kit. MollyMod is MOLYMOD, and you can use that if you're really interested in carrying on in chemistry. Go for it. 5 electron groups is for the honors kids, because then you'd have 10 electrons around, which is a violation of the octet rule, and you would end up with a geometry which is trigonal bipyramid. So you'd have 3 glumps in the equator and 2 glumps in the axial region. PF5 is an example, and then there's an octahedron, which is another one. Octahedral, like sulfur hexafluoride is an example where all the angles are 90 degrees. So if I just quickly sketch it out, fluorine there, then fluorine going back, and fluorine going back. Okay. So more Vesper details. Well, I've already talked about this. You can read it on your own. Here's some pictures at the bottom showing you what I did. There's a simulation on the CHE40 site, which is a good site to look at. All sorts of simulations where you can look at some molecular shapes. So you want to explore that. So in the Vesper game, we're going to draw the Lewis structure. You always start by that because then you can count how many electron groups. In this rules, they talk about high electron density. I'm going to talk about electron groups instead. Single, double, and triple bond count as one region of high electron density or one electron group. An unpaired electron, no, electron pair. Let's just call it a lone pair. Counts as one region. So the better just to do here, number of electron groups is number of bond groups plus number of lone pairs around the central atom. I don't care about the ligand lone pairs, just the central atom. So here's some examples. I made some changes from in your book, so you might want to look at that. I'm going to start with CS2, carbon disulfide. So there are 2 electron groups, it's linear. HCN, 2 electron groups, it's linear. CO2, 2 electron groups, it's linear. Other side, BF3, 3 electron groups, trigonal planar. SO3, 3 groups, it's trigonal planar. Now notice how one of the groups is double bond, but that just counts as one group. So 3 is 3 plus 0, which is 3. NO2 minus, well, here you got 3 groups. You got it 1, 2, 2 bond groups, and 1 lone pair. So the total number of electron groups is 3. So it's 2 plus 1. So the electron group geometry is trigonal planar. The molecular geometry is how the ligands are arranged. Here it's bent. If you have a lone pair in the central atom, then your molecular geometry cannot be the same as the electron group geometry. If you do not have a lone pair, then they are the same. Okay, so that's what we just said on page 14. So I think it's best jump to these examples here. Let me just see if I have something on page 16 that will be more helpful. No, that's polarity of molecules. Okay, so I'm going to sneak in some other examples here. So let's try PCl3, and I'm going to go to the paintboard to do that one. Okay, so PCl3. Let's play the Vesper game. Everything we know about PCl3. So let's start. This is our Vesper game. VSEPR game. So PCl3. First of all, phosphorus is going to be the central atom because halogens like to be at the end. So the Lewis structure, I'll have a phosphorus, I'll have a chlorine, and a chlorine. And I'm going to have 5 plus 21, 26 valence electrons. Halogens only like to be single bonds. 6, 12, 18, 20, 22, 24, 26. So it works. So in playing the Vesper game, the number of Vesper groups is going to be 4, which is 3 bond groups and 1 lone pair, right? 3 bond groups and 1 lone pair. Whenever you have 4 Vesper groups, the electron group geometry now known as the egg, it's faster to write that, is tetrahedral. Okay? There is a lone pair though. If there's a lone pair or more than one, 2 lone pairs, even 3 lone pairs around the central atom, then the molecular geometry can't be the same because you don't have an atom up where that lone pair is. So the molecular geometry in this case, where the egg is tetrahedral, there's 3 bond groups and 1 lone pair, is called pyramidal. Some people are more exact and they call it trigonal pyramidal, but pyramidal is good enough. Okay, so if this is the case, it's called pyramidal. So I'm going to have phosphorus, I'm going to have a lone pair. Often in these drawings you draw the lone pair in this little balloon. Chlorine here, I won't bother around about the lone pairs on the ligands. A chlorine coming out and a chlorine going back. Okay, so PCl3 is an example of a pyramidal molecular geometry and a tetrahedral egg. Ammonia is another example of exactly the same thing. A pyramidal molecular geometry and a tetrahedral egg. Okay, let's go to a new page here, and let's see what the next example was. I guess I want to go here. CS2, we already looked at linear. Let's look at H2CO. Okay, so H2CO, which is formaldehyde. So we've got carbon, oxygen, hydrogen, hydrogen. Here's a Lewis diagram. So carbon's the central atom, so it's 1, 2. It's got 3 bond groups, no lone pairs. So if it has 3 bond groups, the egg is trigonal planar. And there are no lone pairs, so the molecular geometry is also trigonal planar. Okay, so you're going to have C, O, H, and H. Now, I don't have to call this a perspective sketch. I could just call it a sketch. It's not a perspective because it's all in the same plane of the sheet of paper. And the angles are around 120 degrees. Okay, so that's an example of playing the Vesper game for H2CO. Whether the molecule is polar or not polar, that'll be in our next lecture. Let me do one with 3. Let me do ozone, O3. So we've got oxygen, double bond. So here, notice how important it is to know your Lewis diagrams. So the central atom, you got 1, 2, you got 3 groups. 2 of them are bond groups, the double bond and the single bond. Remember, in the Vesper game, the double bond just counts as 1 group, and you got 1 lone pair. Okay, so the egg is trigonal planar. The molecular geometry is bent off of 120 degrees if you want to be really exact, because what you have is something like this. Okay, so you got the lone pair, single bond to double bond. If you want, you can put in the lone pairs on the ligands. Get rid of that one, put it there better. So 120 degrees would be the angle between the lone pair, the double bond, and the single bond. Now, in fact, the lone pair squeezes the angles in together, so the bond angle O is actually slightly less than 120 degrees. Lone pairs are more diffuse because there's no atom narrowing them out at the top, so they take up more space, so they push together the bond pairs more dramatically. If you have 2 lone pairs, they push each other away from each other and squeeze in things even more. That's why, for example, in nitrogen trifluoride, or even ammonia, the angle HNH, that's my symbol for angle, is going to be slightly less than 109 degrees. Let's look at water. Okay, dihydrogen monoxide. So you're going to have, you can draw the Lewis diagram of water as if it's linear, but you know it's not, because the number of electron groups, or number of Vesper groups, electron groups, the number of bond groups, which is 2, plus the number of lone pairs on the central atom, so a total of 4. Therefore, those 4 groups try to get away from each other as much as possible. So the egg is tetrahedral, and the molecular geometry is bent, or angular, or V-shaped. Those are other names for it. Bent, angular, V-shaped. Off of, here it's not off of 120 though, it's off of 109 degrees. 109 degrees is like your standard tetrahedron, and then you're squeezing it a bit more, because if I draw it, there's my hydrogens, there's a lone pair coming out, then a lone pair sneaking back. So those lone pairs repel each other, they squeeze that in. So the angle HOH actually turns out to be approximately 104 degrees, which is less than 109. More lone pairs you have, greater in you squeeze the electrons and the bond angle. Okay, let's go back to the drawing here. So we have some examples. Chart of electronegativity, polarity of molecules. Okay, that's coming up. So get some more practice. There's some sheets on just drawing the valid Lewis diagram, describe the molecular geometry and the egg, give the approximate bond angles. I mean like greater than or less than. I don't mean, you don't have to know that water has a bond angle of 104 degrees. Just know that it's less than 109 degrees. Do a perspective sketch, and polarity we'll get to next time. Okay, have fun.